This is the first of 3 lectures covering the various methods of deconvolution used by GSI. In this first lecture, we look at the preferred method of deconvolution in the wavelet processing sequence, and that is designature. Now, designature is a pre-stack wavelet deconvolution. It has 2 main differences to conventional spiking or predictive deconvolution. The first is that it is just one time-invariant operator which is designed from the whole record, as opposed to a trace-by-trace design in the case of conventional deconvolution. The second main difference is that it collapses the effective source wavelet, that is the reflection wavelet on the input record, to a zero-phase wavelet on the output record. Now, a zero-phase wavelet gives maximum possible resolution for the frequency bandwidth on the output record. It has one basic similarity, however, to conventional deconvolutions, in that it assumes that the input wavelet is minimum phase. Now, designature is part of the wavelet processing sequence based on the convolutional model which has been discussed in previous lectures. And designature is designed to remove, or correct rather, the 2 terms in the convolutional model equation which are underlined here. Ri is the convolution of several things: the short period reverberations, ghosts, and the instrument response. That's really the total recording system response. The other term which designature is designed to correct is W, which is the source wavelet. Now, W of T, the source wavelet, is normally assumed to be minimum phase. If it is not, then some preliminary processing is needed before deconvolution in order to convert the source wavelet to minimum phase. For example, if the data is from a vibrosized source, then a correlation is needed to output a minimum phase wavelet rather than a zero phase wavelet, as with conventional correlation. In the case of maxipulse, for example, the debubble process is required to convert the non-minimum phase wavelet into a minimum phase wavelet before designature. Now, in order to understand the design of designature and the way it operates, it's necessary to understand how the seismic record is built up according to the convolutional model. And the first step in this is to simplify the convolutional model equation somewhat, and really group it together into 2 main sets of terms. Those will be the terms up to here, and then the ones which designature is designed to correct. So we can shorten the model equation down to this, just saying that the seismic record, that would be the field record which we're going to apply designature to, is equal to the convolution of a record which I've called Sn, convolved with the effective wavelet, that is the convolution of those 2 terms. Now, the effective wavelet is the part of this equation which we're trying to correct, so that what we're really trying to get is this term, Sn, which, for want of a better word, I've called a kind of synthetic record with which the wavelet is convolved to give the actual field record. Now, we're going to look at the terms one by one in the convolutional model and see how they are combined to build up, first of all, the so-called synthetic record, and then how the other terms combine to produce the effective wavelet. And we're going to look at the characteristics of these various components in both the time domain and the frequency domain. The first term in the model equation is the primary reflection sequence or reflectivity sequence. R of t is just a function of time. And we can represent this as a spike sequence. Of course, each spike represents a reflection from some interface in the Earth with the amplitudes proportional to the reflection coefficients. Now, the amplitude spectrum of the reflectivity sequence is often assumed to be a perfectly flat, smooth spectrum. In other words, that assumes that the sequence of spikes is purely random. However, this is not quite true in practice because of the finite time length of the normal seismic record, or the portion of the reflectivity sequence that we normally record. So that, in fact, the amplitude spectrum of the reflectivity sequence does show some fairly rapid fluctuations, although it is fairly flat overall. The next term in the model equation is T1, which consists of all the various multiples except the short period shallow reverberations. So that if the first trace here is the sort of primaries only, synthetic, this can be regarded as a synthetic trace with multiples. Now, the addition of the multiples doesn't really alter the basic character of the amplitude spectrum of the trace. Although each multiple is a periodic function, the range of periods of all the different multiples on the trace are fairly randomly scattered, so there's no noticeable periodicity introduced into the amplitude spectrum. It remains fairly flat in general, but not smooth. It shows rapid fluctuations. The third term in the model is the move-out term. Now, the previous traces can be regarded as zero offset traces. The convolution of those with the move-out term produces a multi-trace record with traces of various offsets and with move-out included on the reflections. Now, the amplitude spectrum of any one of these traces would be similar to the previous one in character. However, if we were to take the average of the amplitude spectra of all of the traces, we'd find that it was a flat, smooth spectrum. Now, this is because the individual spectra, although they're like this in general character, are all slightly different, so that when we average them, we tend to smooth out the rapid fluctuations in the amplitude spectrum, resulting in a smooth, flat spectrum. The next term in the model equation is the spreading loss. And the convolution of the three previous terms, which we've just looked at, is multiplied by the spreading loss function, which is really just a kind of amplitude scalar, as depicted here. It has the effect of scaling down the amplitude of the deeper events on the trace, so that the amplitudes of the shallow events are relatively large. We're just looking at one trace out of the set here. Now, this doesn't significantly affect the general character of the amplitude spectrum of the whole record, that is the average amplitude spectrum. It remains fairly flat and smooth. It is, of course, weighted towards the amplitude spectrum of the shallow data now because of the higher amplitudes at the start of the trace. The final term in the first part of the model equation is the absorption effects, T2, sometimes called inelastic attenuation. Now, the inelastic attenuation effect is like a time-variant high-cut filter. On the shallow data, it has a very gentle high-cut effect. As we move down to deeper reflections, the high-cut effect becomes more severe. The effect of that on one of the traces of our record is that it would change the spike form of trace to a continuous function, of course showing amplitude decrease still, and a general lowering in predominant frequency on the deeper reflections. However, this doesn't have any very significant effect on the average amplitude spectrum of the record. It still remains quite smooth and fairly flat. There will be a slight fall off in amplitude at the higher frequencies because of the high-cut filtering effect of the inelastic attenuation effect. However, this is not very severe because the spectrum is weighted towards the high amplitude shallow events where the high-cut effect is least. Well, this then completes the terms which are convolved together to give what I've called the synthetic record, the sort of record that we're trying to find after we've deconvolved or designatured the field record. Now, we've shown then that the average amplitude spectrum of the record to this point in the convolutional model is a flat, smooth spectrum. Now that is multiplied by the amplitude spectrum of the effective wavelet to give the amplitude spectrum of the record, of the input record to designature. Now this assumes that the effective wavelet is identical on each trace, so that we're multiplying the average spectrum, the so-called synthetic, by the wavelet spectrum, and that gives the amplitude spectrum of the average amplitude spectrum of the input record. Now the point about this is that if the spectrum of the record SN, synthetic, is flat and smooth, then the amplitude spectrum of the field record must be identical to the amplitude spectrum of the wavelet because of the multiplication. So this says that we have a means of determining the amplitude spectrum of the effective wavelet. We simply have to measure the amplitude spectrum, the average amplitude spectrum of the input record. Now look at the various components which make up the effective wavelet. The first of these is the source wavelet itself, which is normally a relatively sharp pulse, except obviously in the case of a vibrosized wavelet, say, or maxipulse wavelet. So it has a fairly broad, flat amplitude spectrum. On marine data, the ghost effects are quite significant, and these result in looking just, say, at the source end of the travel path in a ghost pulse following every primary reflection, so that in the frequency domain, this has the effect of introducing notches into the amplitude spectrum. Now ghosting, of course, takes place at both ends of the travel path, at the source end and also at the receiver end. And the effect of that is to introduce a second ghost, which is a ghost of the primary and the first ghost. This, looking at it on the frequency domain, introduces further notches into the amplitude spectrum. Another component of the effective wavelet is reverberations. And reverberations, of course, are a sequence of periodic events following each primary reflection. In the frequency domain, the amplitude spectrum of a reverberation sequence shows a periodic type of fluctuation of amplitudes on the amplitude spectrum. The final main component of the effective wavelet is the instrument response. Now this is mainly simply the effect of the bandpass filters in the recording instruments. So it has a wavelet characteristic something like this and just a bandpass type of amplitude spectrum. The effective wavelet is then the result of the convolution of these various component wavelets, or looking at it in the frequency domain, it's the result of the multiplication of the various amplitude spectra. Now there are some basic differences between the effective wavelet on marine data and on land data as shown here. In the marine case, the effective wavelet results from the multiplication of the amplitude spectra of the source wavelet, the ghost effects, reverberation effects, and the instrument effects, giving an amplitude spectrum for the effective wavelet which in general is something like this. It shows significant notches due to the ghost effect. It shows some minor fluctuations, could become quite large, due to the reverberation effect, and a sort of overall bandwidth mainly due to the instrument bandpass filtering. In the case of land data, the ghosts and reverberations are not so significant, so that the spectrum of the effective wavelet is mainly simply the multiplication of the source wavelet spectrum and the instrument response spectrum. So it does not show the notches due to ghosting or quite so much fluctuation due to reverberation effects. Now, summarizing so far then, we've seen that for Designature, we can assume that the effective wavelet is minimum phase. Remember, this assumes that in the case of sources where the source wavelet is definitely not minimum phase, it has to undergo some preliminary processing to convert it to minimum phase. The other components of the effective wavelet, the reverberations, instrument effects, and ghosts, are all minimum phase wavelets. So the total effective wavelet can be assumed to be minimum phase. The amplitude spectrum of the effective wavelet, as we've seen, can be assumed to be identical to the average amplitude spectrum of the record. So these two assumptions then allow us to determine both the amplitude spectrum and the phase spectrum of the effective wavelet. Once we've found the amplitude spectrum, the minimum phase spectrum corresponding to that can be calculated. Now, looking at how we use the effective wavelet in Designature, it's summarized by these equations. From the point of view of the frequency domain, a simplified model says that the frequency spectrum of the record, the input record, is the result of the multiplication of the frequency spectrum of the effective wavelet and the frequency spectrum of our wavelet, our record SN, which, remember, is the thing we're trying to find after designature. Now, turning this equation around says that the frequency spectrum that we're trying to find is equal to the frequency spectrum of the input record, which of course we can measure, multiplied by the inverse of the effective wavelet spectrum. Now, of course, we can determine the effective wavelet spectrum, as we've already shown, because we can find its amplitude spectrum and from that calculate its minimum phase spectrum. Now, looking at how we accomplish this multiplication in terms of amplitude and phase spectra, remembering this represents a complex spectrum, this complex multiplication simply means that we multiply the trace amplitude spectrum by the inverse of the amplitude spectrum of the effective wavelet, and we subtract the phase spectrum of the effective wavelet from the phase spectrum of each trace on the record. And those two operations effectively accomplish this complex multiplication. Now, looking at the effect of that on the amplitude spectra, the amplitude spectrum of an individual input trace will in general look something like this for marine data, seeing the ghost notches. The amplitude spectrum of the designature filter, remember, is the inverse of the average record spectrum, so it is approximately the inverse of the spectrum of an individual trace. The designature operation effectively multiplies these two amplitude spectra, resulting in this amplitude spectrum for the output trace. Now, the notches and due to ghosting, and the fluctuations due to reverberation, and the general decrease in amplitude due to source wavelet and instrument effects are corrected by designature. The output spectrum is in general fairly flat, but it shows the rapid fluctuations which are part of the reflection sequence, as we've seen that it should do. Now, looking at the amplitude spectrum picture of the reflection wavelets as opposed to the whole trace, the amplitude spectrum of the input wavelet would in general look something like this for marine data, say. The amplitude spectrum of the designature filter is approximately the inverse of this, so that the resulting wavelet spectrum on the output trace, which is the multiplication of these two, is in general a fairly flat spectrum. It shows slight residual notches where the ghost notches occur on the input wavelet, since there is a limited amount of boost or amplification in the designature filter, and it shows a roll-off at the low frequency and high frequency ends of the spectrum due to band limiting in the designature process. Now, looking at the wavelets themselves, the wavelet on the input record would in general be a fairly long reverberating wavelet. That is convolved with the designature filter wavelet. Now, notice that this is a two-sided wavelet. It has significant amplitudes both before time zero and after time zero, whereas the input wavelet, being minimum phase, is a one-sided wavelet. It does not have any significant amplitudes before time zero. The result of that convolution is the output wavelet, which is a zero-phase wavelet, a relatively short zero-phase wavelet. And of course that is the shortest possible wavelet having this amplitude spectrum, and therefore gives maximum resolution on the output record. Now, looking at the operation of designature in a flow diagram form shows the various steps that take place during designature. We start with the input record and simply take the Fourier transform of each individual trace to give what we can regard as a frequency distance domain, where we have the frequency spectra of the traces at each individual offset. So we have the amplitude spectrum and the phase spectrum for each individual trace. Now the amplitude spectra are averaged to give the average amplitude spectrum for the whole input record. That average spectrum is used in two slightly different ways. First of all, a moderate amount of white noise is added to the spectrum, and it is then inverted to give the amplitude spectrum for the designature filter. Remember, we've pointed out that the amplitude spectrum of the designature filter is the inverse of the average amplitude spectrum of the input record. It's not the exact inverse because we've added a moderate amount of white noise before the inversion. This white noise addition is done mainly to ensure that we do not have zero amplitude at any point on the spectrum, because if we did, then we'd effectively be dividing by zero at some point in the inversion, resulting in a blow-up or failure of the filter design. So white noise is mainly a mathematical safeguard to ensure that we don't try to divide by zero at any point. Now the average amplitude spectrum is used in a slightly different way to obtain the phase spectrum for the deconvolution filter. It's first of all modified to some extent. Now this modification simply consists of altering the very low frequency and very high frequency parts of the average amplitude spectrum. At the very low and high frequencies, the average amplitude spectrum is controlled mainly by the noise which is present on the input record. And we simply disregard those parts of the average spectrum and replace them by cutoff slopes which are determined by the cutoff slopes in the instruments and the cutoffs due to ghost effects and so on. So we modify the very low and very high frequency parts of the amplitude spectrum, then add a very, very small amount of white noise, again as a sort of mathematical safeguard. And then from that modified spectrum, we calculate the corresponding minimum phase spectrum. And that computation is done by means of a Hilbert transform. So we now have the amplitude spectrum and the phase spectrum for the designature filter. That filter is applied to the data in the frequency domain, which means that we multiply the amplitude spectrum of each individual trace by the amplitude spectrum of the designature filter. And we subtract the phase spectrum of the designature filter from the phase spectrum of each individual trace. Those two operations give us, in effect, the deconvolved frequency spectra, the amplitude spectra and phase spectra after deconvolution, or after designature, if you like. Those are inverse transformed back to the time domain to give us the output record. So that is the sequence of operations that take place in designature. Now, looking at one or two points about that in detail, the minimum phase spectrum is calculated by means of the Hilbert transform of the power spectrum, that is the square of the amplitude spectrum, after the modifications. When the logarithm of that power spectrum is taken, the numbers of highest magnitude on the log power spectrum are these negative numbers corresponding to the very low power points or low amplitude points on the original spectrum. Now, it is these numbers of highest magnitude which mainly control the phase spectrum that is computed by means of the Hilbert transform. Therefore, in effect, it is the low power points or low amplitude points on the spectrum which determine the minimum phase spectrum that is computed. It's therefore very important to measure both the frequency and amplitude of these low power points on the spectrum accurately. And that is the reason why the amount of white noise that is added to this spectrum before the computation is extremely small. Now, the white noise which is added to the average amplitude spectrum before inversion to obtain the amplitude spectrum of the designature filter has the effect of, to some extent, limiting the flattening or whitening of the output spectrum, and it does that in this way. If we have, say, a very simple input spectrum like this, amplitude spectrum, that has some white noise added to it. We're indicating that we've raised the whole level of the amplitude spectrum by adding a certain quantity of white noise, which in effect is the same amplitude at all frequencies, and then inverting that spectrum with the white noise added. That gives a filter spectrum looking like this. That is then multiplied with the amplitude spectrum of the input record, and the result is this output spectrum. Now, we need to scale that up to bring it to roughly the same amplitude as the input spectrum, but having done that, we can see that it still retains some of the shape of the original input spectrum, but the variations are reduced in magnitude. Therefore, the input spectrum has been flattened out, but not completely flattened. It still retains some of the original shape. So that by adding a moderate amount of white noise to the designature design before the inversion of the spectrum, we do limit to some extent the flattening of the output spectrum. Now, we pointed out earlier on that the effective wavelet is basically assumed to be not offset variant. It's assumed to be the same on each trace that is used in the design of the designature operator. Now, in some situations, offset variance of the effective wavelet does occur, and this can be handled in designature by two different methods. In the marine case, it can be handled by what is called offset-dependent designature. This simply consists of dividing the input record into several sets of adjacent traces. For example, a 48-trace record could be divided into 4 12-trace sets. Now, we design and apply designature to each one of those sets independently. So this will handle a gradual offset variation across the record, such as you may get from streamer depth or water depth variations along the streamer. We can see the need for that offset-dependent designature in this slide, showing the estimated wavelets in designature for a whole record and for 4 quarters of the record separately, as they would be seen by offset-dependent designature. And we see that there are variations in the wavelet shape across the record. And this illustrates the need for offset-dependent designature. The other way in which the designature can handle offset-dependent variations, such as may occur on land data, is to apply two-pass designature. The designature is first of all applied in the fairly normal manner to each shot record, but with the exception that we output minimum phase wavelets rather than zero phase wavelets from designature. The records are then regathered into common receiver records. Designature is applied again to those receiver records, but this time outputting zero phase wavelets. Now the effect of these two steps is that the first one sees the effective wavelet that is common to all the common shot traces, whereas the second step sees the wavelet that is common to all common receiver traces. In other words, the wavelet which is determined by the characteristics at each receiver group. This effectively accomplishes an offset variant designature which will handle fairly rapid fluctuations or random variations from trace to trace.